ADMX's current methods of setting axion coupling exclusion limits. Now, axions arise from a proposed solution to the strong CP problem, which states that there's no known reason why the strong force should conserve CP symmetry, despite always being observed to do so. Axions are pseudoscalar hypothetical particles with an extremely weak coupling to ordinary photonic matter. Now, this, along with their potential mass range, makes them an additional promising candidate for cold dark matter. Of the two benchmark models you can see on the slide, the DFSZ model has the weaker of the two couplings. And it's for this reason that it's seen as the gold standard for axion detection sensitivities. Now, there are other experimental setups used in axion detection, but we'll be focusing exclusively on the haloscope. Now, the haloscope aims to detect dark matter axions originating from the galactic halo. These axions are converted into photons via the Primakov process, which we saw on the previous slide, in the presence of a strong magnetic field inside the haloscope's microwave cavity. Now, these are low-power detections, especially when compared to conventional particle detection methods such as accelerators, with the expected power output of a converted axion being on the order of 10 to the minus 23 watts. The cavity itself can be made sensitive to various axion masses using the internal tuning mode, you can see there. When the converted photons are resonant with the cavity, they are amplified and able to be detected by the radio frequency receiver inside. Now, we work with the ADMX collaboration, who has been collecting axion data using haloscopes since 1995 across a number of runs, and recently achieved DFSZ sensitivity within the last decade. We were given a 10 megahertz wide portion of real axion data from Run 1C, which is ADMX's most recent unpublished data collection cycle, as well as access to their data analysis tools. You can see the limit spectrum for these runs up here. So we wanted to determine if the current ADMX data analysis flow and limit-making methods were valid and appropriate. Let's begin with a rough guide to the data analysis flow. We start with the data recorded from the haloscope itself, which comes in the form of these individual power spectra for narrow frequency bins. These are combined into a ground spectrum using weighting techniques which optimize a signal-to-noise ratio. These ground spectrum frequency bins are then combined into a limit spectrum, which we saw an example of previously, using limit-making methods which we'll discuss more later. You can see from the two equations on the slide that the converted axion power depends on a great number of experimental parameters, as well as on the coupling of the axion itself. And we wanted to then validate the use of these equations in the data analysis flow by analyzing and varying these parameters. So we chose three parameters from the previous equation: the magnetic field B, the geometric form factor C010, which corresponds to a specific mode within the cavity, and the overall haloscope temperature, which can all be theoretically experimentally varied by the experimentalist. Limit spectra were produced for various multiples of these parameters, and the average coupling limit spectrum were plotted. Now, the gradients of the lines of best fit for these graphs should give the dependence of the coupling on the parameter if the equations are used appropriately. And the recovered coupling dependencies were close to the expected values, but for the form factor and the temperature, they're off by over one uncertainty. Now, we could bring these into agreement with their expected values simply by using more multiples of these parameters. So the current axion line shape is completely unknown to us because obviously it's not been detected. And an example of a line shape we search for is the Turner line shape, which incorporates the experimental motion with respect to the galactic halo. And some parameters of this line shape include the Earth's rotational and orbital velocities, the latitude of your position on the Earth, or whatever celestial body you want to put yourself on, and the galactic halo velocity. Here we can see the distribution function for halo axions, with the tallest peak corresponding to being in the galaxy's rest frame, the shortest peak being in the laboratory frame in June, and the central one being the laboratory frame in December. We can use and vary these parameters in order to mimic the conditions found on various extraterrestrial systems, which can then be used to validate if haloscope sensitivity is significantly improved by an extraterrestrial experiment, for example. However, we found that the locational sensitivity of the haloscope is more than lacking. There was virtually no significant change between the limit spectra, which you can see on the right as 4 locations. The limit-making method that we use, the MC method, does introduce these statistical coupling fluctuations, but the size of these was always significantly less than the systematic shift from the change in location. Now, the halo velocity value that we used comes from our current understanding of galactic dynamics. And in the event of a serious misunderstanding of these dynamics, we can see some limit spectra for these values. However, it's not currently known to us why the limit spectra appears to be asymptotic with increasing the halo velocity. So we were given 3 limit-making methods by ADMX, but we chose to exclusively analyze the MC method because this is the one that they use to publish their official results. And we therefore thought it was pertinent to check the function, logic, and structure of this method. Now, notably, this method uses random number generation from Gaussian distributions. And we decided to further investigate this feature in particular, as well as see if we could reconcile to the MC method with a different method, the average method, in order to better understand their differences. So when we modeled the entire ground spectrum of powers against the Gaussian, we found a very poor fit with a chi-square value of almost 3 for its 1 degree of freedom. However, when modeled against the sum of 2 Gaussians, we found a quite positive fit with a chi-square value of 0.23. Now, this doesn't invalidate the MC method just because it doesn't fit this Gaussian distribution, because these Gaussians are actually generated on a frequency bin by bin basis, rather than from the ground spectrum as a whole. For the purpose of merging these ground spectrum bins into the limit spectrum and also to find the 90% confidence limit for the limit spectrum. We also were not sure why there was Gaussianity in the first place, because no analytical techniques used introduced any form of Gaussianity, but it may be central limit theorem induced. We also wanted to see if we could converge 2 of the methods, the MC and the average method, which involved tweaking the method variables, namely the random number generation amount and the smoothing factor. Now, when we changed the amount of random numbers generated, we found that there was no significant change to any of the limit spectra whether we increased or decreased this. However, the smoothing factor affects both methods at the same time. And we can see 2 example limit spectra for different smoothing factors here. And it should be quite plain to see that with a smaller smoothing value, the spectra appear to overlap more strongly. Now, we can take this to its logical conclusion and say that when there is 0 smoothing factor, then the spectrum should match. But this, of course, is going to be true, because that means there's no smoothing at all, and the ground spectrum is simply being returned to us as the limit spectrum. And so we determined that it was impossible to converge these 2 methods without simply destroying the function of the methods altogether. So within the future of the field, recent developments in quantum sensor technology, such as squeeze-state amplifiers and single photon counting techniques, should allow for a near future improvement to the sensitivity of haloscopes through decreasing the electronic noise temperature. Beyond our project, we found that there were a number of avenues for further analysis. We could introduce additional limit-making techniques, one example of which is the Feldman-Cousins method, in order to test the efficacy and appropriateness against the MC method. We also noted that during the analysis there was no accounting for the halo axion's blue shift, and we believe that this is important to future analysis. Additionally, and finally, within ADMX's data chain, rescanning axion candidates is of vital importance because this first pass through a frequency range is not the end. And the methods for identifying and probing these rescan candidates should be stress tested in similar ways to the ordinary limit-making methods. So in conclusion, we found that the current ADMX methods of setting exclusion limits and the data analysis flow are more than appropriate and well motivated, although they could be tested against additional methods in the future. We also found that the halo scopes are largely insensitive to location according to the terminal line shape. And this is good because we can reliably set up halo experiments anywhere on Earth, but it also doesn't give much justification for extraterrestrial experiments, with them being likely costly. We can also say that the methods are unable to converge without simply destroying the function of these methods in the first place. So thank you for listening. I hope you enjoyed. Any questions?
If you had to carry out this experiment on any extraterrestrial body other than Earth, which one would you choose?
So we analysed two alternate ones. We initially analysed another place on Earth, Sheffield. But I say Sheffield because there's plans to build a hill somewhere. But we found that Mercury was our best bet for a very slight improvement to the coupling limits. And we chose Jupiter and Mercury because amongst the solar system's bodies, they have, I think Jupiter has the highest rotational velocity and Mercury has the highest orbital velocity. So I guess Mercury, although that's pretty hard.
Thank you.
I guess just about the operation, I have no idea about ADMX. So how do they operate? Do they run for long periods of time before you get enough data to analyse? Or how
So, from what I remember, they scan very small frequency bands, and I think each scan lasts for 100 seconds, and I think they're over about 100 hertz as well. And then I know that run 1B, which was the previous published data one, I think took 2.5 to 3 years, and that's only for, what, 150 megahertz of frequency space, and the parameter space for the axion mass is huge. It could be anywhere between a few nanoelectron volts to the initially proposed 100 kiloelectron volts way back in 1977, although the bounds have decreased a bit from that value since then.
On the haloscope, so your haloscope, you're looking for a particular resonant frequency.
Mm-hmm.
Does that give you the mass, or does that give you the energy that you'll get from the line shape?
It gives you the mass. So the mass corresponds to the photon's frequency. Although, as I mentioned with the blue shifting of axions, that's not taken into account like as part of the energy of the axion itself. And so these limit spectrum are maybe only slightly off, but they are off from the true frequencies. And there is plans to incorporate the blue shift into future analysis, but it's not been done yet.
Any other questions? No, thanks for you there.